information theory, and probably Dr. Adhikary, maybe you can share your slides just to check if they're working.
Yes, of course. Is it visible?
Yes, very much.
Okay,
Very much.
thanks.
Yeah. Please go ahead.
Okay. So first of all, I would like to thank the organizer for giving me the opportunity to talk here. So actually, I will talk about the possible realization of the first moment of realigned matrix. So this is the title of my talk today. So actually, realigned matrix itself a type of operation, or realignment operation is a type of operation which is not, as far as I know, till now it is not realized in an experiment. So this operation is quite a particular, peculiar, has some peculiar nature. So I would like to explore this peculiar nature of this realigned matrix, and then try to realize it, at least the first moment of realigned matrix, because the first moment, I will show you that this first moment of realigned matrix is very helpful in detecting the entangled state. So basically, the topic is related to the one of the most important problem in quantum information theory, that is the detection of entanglement. So to make this talk complete, so I would like to introduce this the concept of quantum entanglement. Maybe you have heard this definition of quantum entanglement many times in this series of talks. So I would like to repeat it once again. So you know that this type of correlation means quantum entanglement is a type of correlation, and it has no classical analog. So, but since it has many applications in many fields like quantum computing, quantum communication, and many other, or mainly the important thing is the quantum cryptography. So in these areas, these quantum entanglement help us in improving the idea of, or we can take our science little bit forward, but just by using this concept of quantum entanglement. So we need the definition of quantum entanglement, and then I will proceed towards our main topic, that is the realignment operation. So basically, here I will talk about only the mathematical part of the of this fascinating topic, that is the quantum entanglement. So so here, to define the quantum entanglement, let us consider the two subsystems A and B, and let us suppose these two subsystems are described by the two Hilbert spaces HA and HB. So if you are considering it is a bipartite system, then the whole system can be described as the HA tensor HB, that is tensor product of these two Hilbert spaces HA and HB. Now, once we have this composite system, so we can have any state which we denote it as psi AB. AB means there are two parties, or yeah, we have already described up in the first line that it may be two subsystem also. So psi AB is the pure state, and let us suppose it belongs to this composite system HA tensor HB. Now this state is said to be separable if it can be written as the tensor product of two individual subsystems. Okay, so here psi1a belongs to the Hilbert space HA, and psi2b belongs to another Hilbert space HB. So if we can write this equation 1 if composer system is written in this way, then we can say that the state is separable. But if we are not able to write this state psi b in this way, then we can say that the state is an entangled state. So now this is about any pure state. But what happens when we have some mixed state? So in case of mixed state, the separable state can be defined as the convex combination of all product states. Okay, so here you can see that rho ia denote the some system described by the density operator in the subsystem A, and rho ib denote the density operator in the subsystem B. So rho IA tensor rho IB, this gives you the product state. And if you take I from 1 to n, if you take the finite number of combinations are there, like finite number of these product states, then we can take the convex combination of those product state. And if we can write this rho in this way, in the convex combination of the product state, then we can say that the state rho is a separable state. But if it cannot be expressed in this form, then we can say that this state is an entangled state. So from this definition, it is not very clear that how to detect the entangled state, because detection, the word comes here because we are defining the entangled state. Let us suppose if we are not able to define the state in this form, then we can say that it is an entangled state. But the problem is that to show it, that rho is written in this form, that means if you would like to show that rho is a separable state, and if you try to write this rho in this form, then you have to take the all possible form of rho which can be written in this form. That means I mean to say that here this rho I and rho IB can be written in different bases also, and one basis is linked with the other basis just by a different unitary operation. So since one we can go from one basis to another basis, so so this, let us suppose if rho is written in this form pi rho ia tensor rho ib, so it is not clear whether we are going from let us suppose this rho I and rho IB is expressed in the computational basis. Okay, so if we are going to some other basis just by using the unitary operation, it is not known whether the resulting state in that basis is also be written in this form. It may not be written in this form, so you don't know. So this means that you have different expression for rho. This rho, the expression for rho is not unique because the basis is not related with one basis is related with the another basis just by a unitary transformation. So this means that it is not possible to detect entanglement just by using this definition of separable state. So now, if we write the simple two qubit system, so let us consider here the pure state psi AB, which can be written as this alpha 00A plus beta 01 plus gamma 10 and plus delta 11, where 0, 1 are the computational basis, and in this four-dimensional Hilbert space, we have four bases, that is 0, 0, 0, 1, 1, 0, and 1, 1. So here the normalization condition is mod alpha square plus mod beta square plus mod gamma square plus mod delta square, this equals to 1. So if we now choose alpha equals to 0 and beta equals to 0, then you can easily see that this psi AB can be written as 1 tensor gamma 0 plus delta 1. So this means that it is clearly written here as a tensor product of two different subsystems A and B. So if alpha equals to 0 and beta equals to 0, then clearly we can say that this psi AB is a separable state. So now again, if we choose different values of alpha, beta, gamma and delta, and if we choose alpha equals to half, beta equals to half, gamma half and delta half, then we can write psi AB in this form: 1 by 2, 0 plus 1 tensor 0 plus 1 in the other system B. So that means here also you can see that these two systems can be written as a tensor product of the two individual systems. So in this case also the state represent a separable state. So now if you choose alpha equals to 0 and delta equals to 0, So if we choose alpha equals to 0 and delta equals to 0, then you can see here that this psi AB can be written in terms of beta 0 1 plus gamma 1 0. And you cannot write this composite system as a tensor product of the two individual system. So if you are not able to write this, this means that this psi AB is an entangled state. So just by using these examples of the separable state and entangled states, I just switch over to the next slide where we can see that different methods for the detection of entanglement. So now the question is that if we know that this state, if some state is given to you, and if I ask you that, tell me whether this state is entangled or not. Okay, so if this is the question, then how to detect this state, whether this is an entangled state or not? So there are various methods for the detection of entanglement. So the first method comes from this Perez and in 1996, and Horodaki proved the Perez conjecture that if some operation which is known as partial transposition operation, if this operation applies on some individual system, any one of the system, any one of the bipartite system, then then there is some way to see whether this state is entangled, whether this state is entangled or not. So this type of criteria is known as this type of criteria is known as partial transposition criteria. So partial transposition criteria, I will come to this point in the later slide. So the first method for the detection of entanglement is the partial transposition criteria. So in this way, there are many other methods like realignment criteria. So I will talk about this method in detail in this talk. And then we have some other method also, that is range criteria. And then we can construct some positive but not completely positive map. And then we can show that those maps can detect entanglement. Also, we have measurization criteria introduced by Nielsen and Kempe, covariance matrix criteria introduced by Gune, and then approaches. There are some other approaches that that is through the construction of witness operator. So there are various methods, but there are few methods that can be used in an experiment. Okay, so for example, this partial transposition criteria. So if you take this partial transposition criteria, this criteria is very difficult to realize in an experiment. And then realignment criteria. First of all, we don't know whether this realignment criteria is realized in an experiment or not. But I will tell you here that there is a way by which we can realize this realignment criteria in an experiment. So this means that there exist very few criteria that may be implemented in an experiment. So now let us focus on two methods for the detection of entanglement. The first method is partial transposition method, or the second method is the realignment criteria, realignment method. So, so to understand this, let us consider a simple system, that is the 2 tensor 2 system, and this 2 tensor 2 system can be described by this 4 cross 4 matrix. Okay, this is a density matrix rho 1 2, and its element is written like this. So here you can see that this 2 cross 2 matrix can be written in the block matrix also. So here the A, B, C, D, these are the block matrices, and it is defined in equation 7. Okay. So now the partial transposition, what do we mean by partial transposition? So partial transposition means that just take the transpose of each and every block. Okay, so here you can see that A, B, B dagger, and C, these are the block matrices that represent the density matrix rho 1 2, and if you take the transpose of each block, then you can get the partial transposition operation. So after operating the partial transposition operation, then you can find out that this matrix rho 1 2, which is given by 6, it reduces to equation number 8. So this means that this first block T11, T12, T12 star, and T22. So you just have to interchange the off diagonal element for of this block. Okay, so T12 goes towards takes place of T12 star, and T12 star take place the element of T12. So in this way, if we take the transpose of block B and block C and block B dagger, then we can say that this operation is nothing but this operation is known as partial transposition operation, and it is very useful operation because it can detect entangled state. So what is the method of detecting entanglement? So the method of detecting entanglement is that Perez said that just consider any 2 cross 2 system or any m cross n system, and then just performing this partial transposition operation, and then see whether this the resulting matrix also describe a physical state or not. So to describe a physical state, we need to satisfy the following condition. First one, the resulting matrix should be positive semi-definite. Its trace should be equal to 1. Okay, so if we see these two criteria, then it is enough to say that this state is a physical state. Okay, so now here you can see that if we apply this partial transposition operation on rho 1 2, then rho 1 2 reduces to rho 1 2 T2, which is given by equation 8. And to see this, to see whether the state described by the density operator rho 1 2 is an entangled state or not, we just have to find out whether this rho 1 2 T2 represent a positive semi-definite matrix or not. So if rho 1 2 T2 is a positive semi-definite matrix, then we can say that the state rho 1 2 is an entangled state. It is an if and only if condition. That means if rho 1 2 is a separable state, then rho 1 2 T2 is also a positive semi-definite operator. And if rho 1 2 T2 is a positive semi-definite operator, then rho 1 2 is a separable state. So it is an if and only if condition. But this if and only if condition holds only for 2 tensor 2 system and 2 tensor 3 system. In higher dimensional system, it will not hold. Okay, so in higher dimensional system, there also exists some other type of entangled state which violate this condition. So here you can see that so this is the partial transposition criteria, and this is proved by Horoki that this criteria is necessary and sufficient condition for 2 tensor 2 and 2 tensor 3 system. So now let me talk about something, the realignment of a density matrix. So what do we mean by this? So here you can see that in the partial transposition operation, we can just change the matrix element in some way, in just following some rule. So here also in the realignment of a density matrix, we are also following some rule, so by which we can change the elements of a density matrix. So this type of changing is proposed by K. Chen et al. And O. Rudolph independently to study the entanglement detection problem. So what we can have just by changing this element, just by changing this element in the density matrix, we can just detect the state, whether the state is entangled or not. Okay, so here in partial transposition criteria, we need to show that this rho 1 T2 is a positive semi-definite matrix. This means that its all eigenvalue should be positive if the state is separable. So now, in case of realignment of a density matrix, we have to change the criteria. The criteria here is that the trace norm of the realigned matrix should be less than equal to 1. So if this hold, then we can say that this state is separable. So one more thing, this realignment, in the case of realignment of a density matrix or realignment criteria, the condition is not necessary and sufficient even for 2 tensor 2 system. This necessary and sufficient if the condition is not necessary sufficient condition, so it is only this condition tells that if rho is a separable state, then the trace norm of rho r, that is the trace norm of the realignment matrix, should be less than equal to 1. So this means that if you know that the state is separable, then why you are applying this criteria? So we can apply this criteria if we go just by if we restate the criteria in this way. So if rho is separable, then norm rho r is less than equal to 1. So other way we can say it like this. If norm of rho r, that is trace norm of rho r, is greater than 1, then the state is entangled. Okay. So now we can use this criteria. So now we have some mathematical inequality. And if we use this inequality, then we, if some state just satisfy this inequality, that is norm rho r is trace norm rho r is greater than 1, then we can say that the state described by the density operator is an entangled state. Okay. So now the problem is that this norm, trace norm, how we can implement it in the laboratory. So this is the problem here. So now I will discuss it later. So this problem, so how to bypass this problem. Okay. So now let's go to the realignment operation. What do we mean by realignment operation? So like partial transposition operation, here also we can change the matrix element of this density matrix element. So what is the particular way of changing the density matrix element? So the way realignment operation is saying is that just take this T11, T12 star. This, you can just take this as a vector. Okay. So you can just consider T11 and T12 star, 12 star as a vector, and T12, T22, the first two rows, take the second column of first two rows, the T12 and T22. Then T13, T23, they take two elements, first two elements of the third column, and T14, T24, these are first two elements of the fourth column. So in this way, we can just arrange these elements as a vector. Okay, T13 star, T14 star, T23 star, T24 star, T33 and T34 star, and T34 and T44. So all these two elements can be described as a vector. Okay. And then take the transpose of those vectors and just form a row. So let us try to construct the first row of the realigned matrix. How to construct that one? So we can construct this in this way. Just T11, T12 star, we can consider it as a vector. Just take the transpose of it. So if you just take the transpose of it, then T11, T12 star will become T11, T12 star in the row. So you can see here that T11, T12 star, which is in the column, now it is in the row. Okay. Then take the first two element of the second column, T12 and T22. We consider this also as a vector, and then take the transpose of it. So if you take the transpose of it, then you can get T12, T22. So this means that the first two elements of the first column, it becomes the first two element of the first row, and first two element of the second column, it will become the first two element of this first row. So in this way, we can form the other rows also. So here you can see T13, T23. So this is a vector, and take the transpose of it, and it will constitute the first two element of the second row, T13, T23, and then T14, T24. If you take it, then it will give you the second row. So in this way, you can form the third row and fourth row. So this type of arrangement is known as realignment operation. Okay. So in this way, we can have the realigned matrix. Okay. And if you take the norm of this, and if the state rho 1 2 described by the density operator rho 1 2 is separable, then norm of rho 1 2 r is less than equal to 1. Trace norm, mind it. This is trace norm. Trace norm of rho 1 2 r is less than equal to 1. So now, if this realignment matrix, and take the norm, trace norm of this realignment matrix, and if you find that this trace norm is greater than 1, then we can say that the rho 1 2 is an entangled state. So this is the thing. But the problem, what is the problem? Problem is that here, in case of partial transposition operation and realignment operation. So in the partial transposition operation, this is a positive operation, but not a completely positive. That means the partial transposition can be considered as a map, which is a positive, but not a completely positive map. Okay. So because transposition operation is always positive. It will not change the eigenvalues. Okay. So if some matrix, positive semi-definite matrix is given to you, just take the transpose of it, and then you will get again a positive semi-definite matrix, because its eigenvalue will not change. But if you take the partial transposition operation, then also since it involves the transposition operation, so it will give you the positive map, but not a completely positive map. I will define the completely positive map in the later slide. So, but now there is a difference between the realignment operation and the partial transposition operation. What is the difference? The difference is that whenever you are getting this rho 1 2 R from rho 1 2, then you can easily see, or you can just take any matrix and then just perform this operation. You can have, you can just find out the eigenvalues of rho 1 2 R. You can find that the eigenvalues of rho 1 2 R may be positive, maybe negative, or maybe imaginary also. So this means that this realigned matrix is neither a positive map, is not a positive map. Okay, so if it is not a positive map, then there is no question of getting the completely positive map. So this is the difference between these two. So, so that means that is why this rho 1 2 R is very hard to realize in an experiment comparatively in comparison to partial transposition operation, because partial transposition operation qualified one test, that is it is a positive operator at least, but rho 1 2 R, even it is not a complete, it is not a positive operator, it gives you a negative eigenvalue also. So now our task will be to to attack this type of problem. Okay. So to do this, let me first define these positive and completely positive maps. So as we had already seen that positive maps are detectors of entanglement, like partial transposition map. It is a positive map and it can detect entanglement. However, if this map is only positive, then it may not be implementable in an experiment. It is very difficult to realize in an experiment, because completely, if some we have some completely positive map, then completely positive map may be implemented in an experiment, but not positive maps. So completely positive map, this in this sense, completely positive map play an important role in quantum information theory. Okay, so now let us define what do you mean by completely positive maps. So if we are considering the composite Hilbert space of dimension n, and let us suppose BH, and BH is the set of all bounded operator in the Hilbert space H, and the elements of this bounded operator is the n cross n matrices in the field of complex number. Now we can define this map, linear map. And this linear map phi can be defined in this way from BHA, that is the set of all bounded operator from the Hilbert space HA to the set of all bounded operator in the Hilbert space HB. So now this map is positive if we consider any element from BHA. So let us take rho belongs to BHA, and if this phi acting on rho, and this phi rho is also positive. Okay, for each element rho belongs to BHA. So if this happens, then we say that the linear map phi is a positive operator. Okay. So now what do you mean by completely positive map? Completely positive map phi is defined in this way. Just take the tensor product of kth order identity matrix with the phi, positive map phi. So IK tensor phi can be defined, the IK tensor BHA goes to IK tensor BHB, and this IK tensor BHA can be considered as MKBHA, MKBH to MKBHB. If this map, if this map is also positive for each positive phi and for each k, that means you can consider the identity operator of any order. You can consider the identity operator of order 2, order 3, order 4, like this. So if you take identity operator of any order, and if you find that for all order identity matrix, this map is positive, then you can say that the map is not only positive but also completely positive. So you can say here this completely positive, to show the map, to show a map completely positive is very difficult, because you have to show for each and every k, IK tensor phi is positive. Okay, so we have some result in linear algebra that makes our path comfortable. Okay, so we will use this to show, we will use those results to show that the map which we will construct, that is completely positive. So just by giving this definition of positive and completely positive map, let's move towards that why completely positive map is important. Okay, so completely positive map is important in this sense. in this sense that CP maps, completely positive maps, are capable to describe an arbitrary quantum transmission channel. So when you were constructing some transmission channel, that transmission channel is completely positive maps, and that is physically realizable. So that is why CP map is important. Also, you can see some unphysical transformations are there. That is, quantum cloner is there, universal NOT gate is there. So those unphysical transformations can be approximated optimally by an optimal CP map. So this is shown by J. Furasek in 2001, and that is why CP map is important, and we use the CP map in our entanglement detection problem also. So now we will use a different type of approximation here, that is known as structural physical approximation. So to realize the realignment operation or partial transposition operation. So since we know that these two are unphysical operation, and since these two are unphysical operation because they are not completely positive, because one operation, that is partial transposition, it is positive but not completely positive, and realignment operation, it is neither positive nor completely positive. So both of these operations are unphysical. So since these operations are unphysical, so we need to approximate it in some way so that it will become a physical operation. So SPA, that is structural physical approximation, is a transformation which goes from positive map to completely positive map. And a physical way by which positive maps can be approximated by completely positive maps is called structural physical approximation. This is a basic definition of structural physical approximation. So now, what is the idea behind this structural physical approximation? So the idea is that let us consider a positive map phi. Okay. So if you are considering the positive map phi, then just mix this positive map phi with some proportion of maximally mixed state. Okay. So here you can see in equation 11, this is the positive map phi. So phi rho, and this id square, this d square dimensional system, because we are considering here d tensor d dimensional system. So the identity operator in d tensor d dimensional system is id square. So this id square represents a maximally mixed state. Okay. So since it represents a maximally mixed state, so we have to add some proportion of this maximally mixed state so that this operation, this operator, positive operator, will become a completely positive operator. Okay. So this is the idea behind this this structural physical approximation. So now, just by realizing this approximation, so let me give you the mathematical interpretation, or what does this mean? How, what happens to the vector when it is when this structural physical approximation applied on some positive pure state or mixed state? So whenever we are considering a pure state, it represents a vector, and whenever it is a mixed state, it represents a matrix. So what happens when we apply this structural physical approximation on this state rho? This means that whenever we are doing this operation, structural physical approximation, it keeps the direction of the vector unchanged. That means the direction of the vector is not changing, but the what changes. So the changes takes place in the magnitude of the vector. Okay. So the length of the vector will be changing by some factor. Okay. So just by doing this, just by changing the length of the vector by some factor, we can make a positive operator a completely positive operator, a positive map a completely positive map. Fine. So this is the mathematical way of defining this structural physical operation. So you can view it like this. So then after gaining some knowledge about the structural physical approximation, let us apply this approximation to the partial transposition operation, which is a positive but not a completely positive map. So here, to see that it is not a completely positive map, you just consider a 2 cross 2 identity matrix, and you can find that I2 tensor this. Here you can see, you can just take the transposition operation capital T in place of phi, and then take k equals to 2, and then I2 tensor T. If you take this operation I2 tensor T, then you can see whenever I2 tensor T operate on a density matrix, you know that density matrix is a positive operator, semi-definite matrix. So I2 tensor T, when applied on this row, then the resulting matrix will not be a semi-definite matrix. It will give some eigenvalue negative. So this means that there exists some integer k for which the transposition operation or partial transposition operation is not completely positive. Okay, so partial transposition operation is positive but not completely positive. So that is why we make it, we have to make it the completely positive. Okay, so to make it completely positive, we need to apply this method that is called structural physical approximation. So here you can see that let us consider any density matrix rho AB and just apply this partial transposition operation on rho AB. So whenever I tensor TB means we are applying the transposition operation on the system B. So whenever I tensor TB operating on rho AB, then the resulting state will be I tensor TB rho AB. Okay. Then what we will do? So then after getting this partial transposition operation, we just mix this partial transposition operation with some proportion of the identity matrix. Okay, that is the maximally mixed state. And then in this paper, this Horodecan occurred, you can see that there exists some proportion by which this I tensor TB will become positive also. So this means that it is a completely positive map. So now, what is the reason behind this? How we can get, what is the reason that if you add some proportion of the maximally mixed state to this positive operator, partial transposition operator, then it will give you a completely positive operator. The reason behind is that the positive eigenvalues of the maximally mixed state, because you are considering the identity matrix, and identity matrix is nothing but it is a completely mixed state, maximally mixed state. So since identity matrix, it all its eigenvalues are 1, that is the maximum eigenvalue 1 if you make the state normalized. Okay, so maximum value is 1. So whenever I tensor TB produces some negative eigenvalue, then whenever you are mixing some positive operator, some proportion of the positive operator with this negative operator, indefinite operator, it may have positive or negative eigenvalues both. So whenever you are mixing this identity matrix with the indefinite matrix, then there exists some proportion. You can adjust that proportion, and just by adjusting those proportion, you can make all the eigenvalues positive. So that means you are just structural when you are applying the structural physical approximation, this means that you are applying some induced map which is of this form: I tensor TB. So whenever you are applying this induced map on I tensor TB, so then this induced map will give you all eigenvalues positive. Okay, so then the question is that if I make it a completely positive map, then what is the role of the partial transposition operation? Because I'm saying this, I'm asking this question because whenever you are applying the partial transposition operation, which is introduced by Perez, so according to Perez and Horodecky, whenever we are applying the partial transposition operation, the resulting matrix will give you a negative eigenvalue, and that is the indication of the presence of the entanglement in the system. But whenever you make it completely positive, so that means whenever this partial transposition operation changes to the structural physical approximation of partial transposition operation, then that may be you may that you may implement it in the laboratory, but always it give you the positive eigenvalues. Okay, so whenever you are applying the SPA map on PT operation, partial transposition operation, then the resulting state will become a positive semi-definite operator. So whenever it is a positive semi-definite operator, it will never give you the negative eigenvalue. So if it will never give you the negative eigenvalue, how you can detect the entanglement? Because partial transposition operation, from partial transposition operation, the negative eigenvalue indicate the presence of entanglement. But here, whenever you are applying the SP of PT, maybe you may realize in an experiment, but it will lost, means we lost our detection method, but actually it is not. Because in case of this SPAPT, this Horodoki and Eckert have shown that there exists some critical value of the positive eigenvalue, and beyond which the state gives you the separable state. For two tensor 2 system, if you consider the 2-qubit system, then here Horodoki and Eckert have shown that the minimum eigenvalue of this SPAPT map, after applying this SPAPT map, the resulting state have positive eigenvalue. So the positive, they have restriction on the minimum positive eigenvalue. So if the minimum positive eigenvalue is less than equal to 2/9, then the state is entangled. So so they have proved this criteria. So that means whenever we are applying the SPAPT map, it also gives you the detection criteria, and also it is implemented in the laboratory also. Okay, so this means that both we have achieved. So both properties we have achieved in this case, this applying the SPAPT map. Okay, we can detect the entanglement just by seeing the minimum eigenvalue of SPAPT map, and also it is implemented in the laboratory. So just by seeing this beautiful approach of SPAPT, we thought of applying this SPAPT on partial transposition operation. But before we proceed towards the SPAPT operation, SPA of the realignment operation, let me discuss about the application of SPAPT operation. So here we have few works on SPAPT. So we can increase the optimal singlet fraction. So optimal singlet fraction is a very useful quantity in teleportation. So we can show that minimum eigenvalue of SPAPT can be or optimal singlet fraction can be expressed in terms of minimum eigenvalue of SPAPT. Okay. Also, we can show that this optimal singlet fraction can be realized using this Hong-O-Mondel interferometric with only 2 detectors. Okay. Not only that, we can estimate negativity just by using this SPAPT map. We also have shown that SPAPT map helps in the detection of entanglement for QIQT qubit system. This is not a D-tensor D system, but it is something M-tensor N system, and the simplest one is QIQT qubit system. So we can use this SPAPT map to detect entanglement in QIQT qubit system. Also, it is useful in classifying the inequivalent classes of 3-qubit system. Also, we have shown that it may help in the quantification of entanglement also. And we have proposed a measure of entanglement that is based on this SPAPT map, and that is that may better work comparative to the negativity. Okay, so all this application motivate us to apply this SPAPT map on realignment operation. Okay, so now here you can see once more just I can explain this realignment operation, and I am now explaining this realignment operation in some different way. So earlier we have just we have considered this realignment operation just by considering the first 2 elements of the first column as a vector, and then we can rearrange in a row. So here you can get the same type just by using some other operation. Okay, so you can do, you just change these two columns, second and third column. Okay, so you just change the second and third column, and then take the partial transposition operation, and then again change the partial second and third column. So in the first step, change the second and third column. In the second step, take the partial transposition operation, and in the third step again change the second and third column. Then you will get the same row 1 2 r as given in 17. Okay, so this is the mathematical way of looking this row 1 2 r. But this can be realized in an experiment also. Okay, because this changing of these two columns can be realized by swap operator, and the partial transposition operation, moment of partial transposition operation, can also be realized in an experiment, and that has been shown in few papers. Okay, so this means that in this way we can just realize the realignment operation in an experiment. So I'm just saying this in this way, but we will work on this. So we are working on this, and we will soon post it in the archive, that how to realize realignment operation in the in a physical way. So here also we had already motivated why we use the realignment operation, because realignment operation is more powerful than the partial transposition operation, because partial transposition operation only detect NPTES, that is negative partial transpose entangled state. But realignment operation not only detect NPTES but also PPTES, positive partial transpose entangled state, that is bound entangled state. Okay, so now how to apply the structural physical approximation on the realignment map. So in the first step, what we had done, we just use the approximation of the non-positive realignment map with the positive map. Okay, so and in the second step, the obtained map, positive map, we have to show the obtained positive map is also completely positive. So that means, again, I'm just simplifying this procedure. So we know that realignment map is a indefinite matrix. Realignment, after applying the realignment map, the resulting matrix will be indefinite. That means it may give you negative eigenvalue, it may give you positive eigenvalue, and both it may give. It also may give imaginary eigenvalue also. But here we restrict ourselves only the real eigenvalues of the realignment map. So first of all, what we have to do, we have to make it positive, and then we have to make it completely positive. So in the two process, first we have to make it positive map, and then we have to make it completely positive map. So to do this, we just applying this structural physical approximation, and then we write this as this: P by D square ID tensor D plus 1 minus P by trace R rho into R rho. So here you can see that this trace R rho, this means that this also can be viewed as a first moment of the realigned matrix. So it is the topic of my, it is the title of my talk, that how to realize this first moment of the realignment matrix. It is just not a mathematical tool, just you got this R row and just take the sum of the all diagonal elements and you will get trace R row. But experimentally it is not, you cannot do it like this. So you have to show some procedure to realize it in an experiment. Okay, so our task is to show that how to find out the first moment of the realigned matrix. So this is the structural physical approximation, and since it may give negative eigenvalue and positive eigenvalue, first we make it positive eigenvalues, so that a positive map. So R tilde rho is positive whenever P belongs to 0 1, if R rho is positive. So whenever you are considering that R rho of that, is after applying the realignment matrix, realignment operation, R rho gives all eigenvalue positive. So that means we don't need to make it positive again, because it is already positive. Okay, but if it gives you the negative eigenvalue, then you have to make it positive. So there are two cases. First of all, if R rho have all eigenvalue positive, then this map holds for all P belongs to 0 and 1. But if R rho gives you the negative eigenvalue, then this R rho R rho will give R tilde rho is positive for some values of P. So here, one more question we can ask, that how to determine the sign of the real eigenvalues of R experimentally without directly computing its eigenvalue. So that means you have some matrix. After applying the realignment operation, the rho, the density matrix will reduces to R rho. So now, since it is a matrix, so how to calculate its eigenvalue? Okay, so how to know that all eigenvalues are real? Or how to know that all eigenvalues are positive, or it may give you the positive or negative eigenvalue? So you can do it just by using the characteristic equation. Okay, so the characteristic polynomial of R rho is given by this. So here you can see that the characteristic polynomial of R rho is given by summation k equals to 0 to d square. We are considering the d tensor d system. So here k runs from 0 to d square, and that characteristic equation is given by minus 1 to the power k a k x to the power d square. This is the characteristic equation. Not only that, just if you have some matrix, then a matrix, then just take the determinant of a minus lambda, where lambda is the eigenvalue of a. Okay, so if you take this, if you just put it equal, if you just equate it to equal to 0, then it will give you the, you will get the characteristic equation. So now, whenever you have this characteristic equation, how to know that this characteristic equation gives you all eigenvalue positive, or it is a mixture of negative or positive eigenvalues? So you can just by you can find out just by Descartes' rule of sign, and here we will show that that means Descartes' rule of sign you can apply on this coefficient ak. Okay, so if these coefficients you know these coefficients, then you may say that whether gives you the positive coefficient or negative coefficient. According to this, you can calculate the change of sign in the characteristic equation. Okay, so that means all reduces to find out this ak. Now we have shown that this ak is nothing but it may be related to the moments, various moments of the realigned matrix. Okay, so this is mi r rho. Mi r rho is nothing but the ith moment of the realigned matrix r rho. Okay, so that means it reduces to the finding out the different moments of the realigned matrix. Okay, so now our task is to, here we will show that we are able to find out the first moment of the realigned matrix. So here we have shown that positivity of R tilde rho, and R tilde rho, when it gives you the negative eigenvalue, then it will give you the positive eigenvalue in for some value of p whenever p belongs to L and 1, where L is given by this expression 24. So now also we have shown that this R tilde rho is also a completely positive map. And then we have this criteria for realignment criteria. So here we have some different realignment criteria, and you can see here that if any quantum system described by a density operator rho, which is a separable state in D cross D system, then norm of R tilde rho sep 1 is less than equal to this quantity. So here you can see that the detection criteria involves the first moment of the realigned matrix. So that this means that if you want to realize this separability criteria, then we need to calculate this first moment of realigned matrix. So if we do this, then we are done. Okay. So now, since theorem 2 gives you the only this condition, that if rho is separable, then this 28 equation hold. Okay, so we have the corollary that if it is this inequality, 28 inequality given by 28 is violated, then this state is an entangled state. Okay, so we can use this. So now let me show you this illustration. So this is a bound entangled state, and this is shown by Powell Horodoky, and this bound entangled state is also verified by our criteria. Okay, now estimation of the first moment of R rho. So here you can we can show that this first moment can be realized in this way. So we have already already know that realigned matrix is given by this R tilde rho AB. In terms of R tilde rho AB, we can write first moment of realigned matrix, which is given by M1, that is trace of R rho AB, first moment of the realigned matrix. This can be approximately related with this one, trace of R tilde rho AB minus P by D square. This means because R rho AB is proportional to this one, it is R rho AB. If you multiply this some normalization constant, then you will get R rho AB. Okay, so that is why I have written here proportional to. So now first moment of this is approximately, since it is proportional to, so we have written here approximately. So M1 is approximately equals to this matrix R tilde rho AB minus P by D square I D tensor D into P. P is some permutation operator. So now after doing some algebra, then you can write this R tilde rho AB into P. And now we know that R tilde rho AB, this is a completely positive map. So it can be realized in an experiment. So since this can be realized in an experiment, so we can have the bound of this M1, that bound of this first moment of realignment matrix in terms of this moment trace of R tilde rho AB into P, which we denote it as S. So here you can see that our M1 first moment is related with the first moment, the bound of first moment is given by this equation 39, that is FLS and FUS. And in case whenever this condition hold and whenever this condition hold, the moment is bounded by these two bounds. So here FLS, FUS is explicitly calculated. So this, in this way, we can have find out, or we can calculate the first moment of the realigned matrix in an experiment. Okay, so so this is the motivation. This is the our conclusion is also this much, that we need to calculate the first moment of realigned matrix R rho, and we have estimated it, and this may be used in this entanglement detection criteria, so that we can have some implementable detection, entanglement detection criteria. Okay, we can implement it in the laboratory. Thank you.
Thank you, Satyabrata, for this interesting talk. Time for questions. Any questions? If so, please unmute yourself and ask.
Well, I have a question. So,
Okay.
Now, this like partial, there are many ways how this partial transposition is incorporated into this entropic uncertainty relation and variance-based uncertainty relation to detect entanglement in labs. I wonder, like, can we implement these realignment criteria using these entropic or variance-based uncertainty relations to detect entanglement?
Okay, good question. So I think you can do this, but the problem is that the realignment criteria itself is not realizable till now. Okay, because this, you can see means you have already seen here that this is some permutation of this matrix element. Okay, so how to realize it in an experiment? So if you are able to realize it, because you need whenever you are applying this in an uncertainty relation, you need to first find out the realigned matrix. Okay, so if you are able to find out the realigned matrix physically, then you can do it. And till now, as far as I know, there means people are saying that it is not possible to realize in an experiment, but I think it is not. We can do it, and we can do it physically, or physically we can show that realignment matrix can be realized in an experiment. So first of all, you need to show that realigned matrix can be realized in an experiment, and then you can apply this in any criteria, either entropic uncertainty criteria or any other criteria. And this is the new thing. Realigned matrix is realigned operation. It is not very useful, not very used in an not very used because it is not realizable in an experiment till now. That is why people are not using. But once you have shown that it can be realized in an experiment, then you can take this realignment operation, or you can use this realignment operation in many places.
Any
Thank
other
you.
question? If not, Somebody has a question? Hello?
Hello.
Yes.
So we saw that after performing this SP approximation, the partial transpose become a completely positive map. So can we use this partial transpose operation as a quantum channel because it is a CP map?
Yes. You can apply there.
So
Because
if so,
it now gives you the completely positive map.
okay. So if so, then what will be the dynamics of entanglement and other correlations?
So you can study this thing. Okay, it is not studied till now, so you can study.
Okay, thank you.
Actually, this SPA, structural physical approximation, is not very means people are not used in recent times. But if you find that we have worked in few places. So that optimal singlet, to increase the optimal singlet fraction, to quantify the entanglement, to detect the entanglement, we have used SPA. But in the past, people have used not very used this process, this method actually.
Okay.
Okay. If there are no further questions, we thank Dr. Adhikary again for his time.
Oh, I